Let's apply Filb to look at forces on current carrying wires due to magnetism in several common scenarios. Before we start that, I want to refer back to the previous video and clear up a point of confusion there, or at least a point that I was confused about for a moment. Our drift velocity definitely pointed straight down, and we had this product dqvd, which I was asserting was equal to idl, and then got kind of concerned about the sign issues. So here's the clarification. This fixes it. dq is negative, since these are our electrons that are moving here. So although vd points down, dq times vd, dq is negative, so that flips the direction of that vector. So this vector, vd times the scalar dq, points opposite the direction of that. dq flips it, so that points up. So it is indeed true that idl is equal to dqvd. Both those point up, and there's no additional arbitrary signs to add in here to fix things. Everything was fine as it was in that video. Okay. First scenario we're going to look at is the possibility that a current carrying wire could be levitated if you put it into an external B field. So in this picture, let's imagine that gravity is pulling down in this direction on this wire, and that this wire here has mass and a linear mass density, lambda, dmdl, mass per unit length, and suppose it's uniform for that orange copper wire here, which is connected to these other green wires. So the orange copper wire, dmdl, is uniform, which implies that we can express the mass of that wire as lambda times capital L, the total length of that wire. So let's say capital L is this total length right there. So then in our free body diagram for this wire, we would have a force of gravity pulling down, so the wire should drop. If, however, this section of wire is connected by some other wires to an EMF here that's driving a current, then we have a current running to the left through this wire, and now we've got a current carrying wire in an external magnetic field. And according to IL cross B, there should be a magnetic force on this orange wire here. Okay, so if the current is running to the left, and then this L vector points in the direction of the current. So IL is kind of a unit here. L goes with the current, so IL crossed with B, thumb is pointing up. There would be a magnetic force up on this wire. And if the B field is strong enough, it's possible that those two forces could balance. So let's state the condition that would be. We want to have the force of gravity balancing our magnetic force, so our wire would levitate here as long as the current was running through it. So force of gravity equal to that magnetic force on our wire. I don't really want to call it a magnetic force because, as I went to pains to argue in the previous video, it's not actually a magnetic force. It's actually an electric force that has the same size as this magnetic force here. So let's just call it the force, the upward force due to the current in the wire. Let's set those two magnitudes equal. So force of gravity is going to be the mass, lambda L, times little g, equals, and then this will be the current times the length. And now here's an important point. This length is the length of wire that's in the magnetic field. Note that the right and left ends of the wire are outside of the region where the magnetic field is confined. The only section of the wire here, the only section of wire that's in the magnetic field is this section. Let's call the width of that section, or the length of that section, W instead. The section of wire actually experiencing the magnetic field has length W. That would be the appropriate length to use right here. So this would be I times W times our magnetic field strength. So I really wanted to emphasize the difference between the full length of the wire and the portion of the length actually in the field, that's what appears in the Filb equation here. That's what appears right there. Okay. Next example. Two parallel wires. So no external magnetic field this time. Let's just have two wires separated by some distance d, both carrying currents to the right. They could be different currents, but both going to the right in this first case. Next, we'll look at that case over there. All right, so let's say our top wire carrying current to the right. We know it'll generate a magnetic field in the region around it. We can imagine grabbing onto that wire with our thumb pointing in the direction of the current, and our fingers curl around in the direction of the magnetic field that that wire is generating. I'm going to indicate that field with in pink here, so that field should be coming out of the board up in this region and into the board everywhere down below it. So that's the magnetic field from wire 1. So that's B from wire 1 right there. Okay, so now wire 2 carrying current to the right is located in the magnetic field being created by current 1. So we know the expression for the magnetic field strength of the field created by current 1. We've solved this both from Biot-Savart law and Ampere's law. Mu naught times current 1 over 2 pi. And if we want the magnetic field at the location of wire 2, that is a distance d away from wire 1, then we would put 2 pi d in our denominator here. That's the magnetic field due to 1 that wire 2 is sitting in. So the magnetic force on wire 2 due to wire 1, I can't help but say magnetic force, even though as we discussed, it's not actually a magnetic force. Anyway, the force on wire 2 due to wire 1, Filb here will be due to the current in wire 2 times the length of wire 2. Let's say they both have this length, capital L, right there, times the magnetic field that wire 2 is sitting in. That would be the field created by wire 1. Okay, so putting those two expressions together, we would have mu naught times I1 times I2, the product of those two currents, times L, all over 2 pi times the distance between those two wires. This is often expressed as the force per unit length, lowercase f. Force per unit length on 2 due to 1 is that force divided by the length of the wires. So there's a constant, the mu naught over 2 pi, that involves the product of the currents divided by the distance. So there's some similarities here to Newton's law of gravity or to Coulomb's law for electric forces. The force depends on some constant, a unit conversion factor, the product of properties of the individual objects. So for gravity, this would be mass 1, mass 2. For an electric force, this would be Q1, Q2. Here for this magnetic force between them depends on I1, I2. But this time it's not an inverse square force law. It goes like 1 over the distance between them, not 1 over the square of the distance between them. So that's a difference from Coulomb's law and from Newton's law of gravity. Okay, how about the direction of that force? Let's see, we should be doing IL cross B. So I for wire 2 is to the right, IL, so IL is to the right, cross with B, B is into the page, so IL cross B, thumb is pointing up. The force on 2 due to 1 is pulling upwards, pulling wire 2 towards wire 1. Okay, that's the force on 2 due to 1. Let's look also at the force on 1 due to 2. So 2, with its current going to the right, is generating its own magnetic field in this environment. So grab wire 2, thumb in the direction of current 2, fingers curl in the direction of the magnetic field it's generating. So wire 2 will be generating magnetic field like this, out of the page everywhere up here, and into the page everywhere down there. Note that in the space in between the two wires, their fields are opposing one another, potentially canceling out. But in the space above both wires, their fields will be adding up, both fields out of the board. In the space below the two wires, the fields are adding up, both fields into the board. So this in blue is the B field being generated by wire 2. So wire 1, sitting in the B field generated by wire 2, is going to feel a force, Filb, so IL cross B. So I1, L in that direction, crossed with the magnetic field generated by B, which is out of the board, so IL crossed with B, that's going to give a magnetic force pointing down on wire 1. And that should not surprise us, because by Newton's third law, we would be expecting equal and opposite forces on those two wires. Just as wire 1 pulls wire 2 towards it, wire 2 pulls wire 1 towards it. So the wires actually attract. Takeaway here is that current carrying wires, parallel current carrying wires carrying current in the same direction, will pull towards each other. So a bundle of wires all carrying current together will sort of pull itself together. It'll tighten and compress as long as those currents point in the same direction. You could just flip the ones and twos in these equations to find that F12 would of course be the exact same magnitude as F21. It would be the same argument, just replace these ones with twos and the twos with ones. We'd get down to this same expression. This valuable result for the force per unit length that two parallel current carrying wires will exert on each other. So that would be newtons per meter, would be the SI unit there. What if the two wires or if the two wires have currents running in opposite directions? I won't run through the math here again. That won't be necessary. Let's just think about the directions of the fields they're generating. Current 1 is the same as before, so that'll be creating magnetic field like this. So wire 2 is going to feel a force in that field, Filb. So IL for wire 2 crossed with B. B is the B created by wire 1 is into the page, so IL cross B, that is going to be pointing down. Wire 2 feels repelled by wire 1. Okay, let's look at the magnetic field created by wire 2. That should be pointing into the page everywhere up here. Into the page. X is for into the page. And out of the page down there. So look, in this case, if the wires are carrying current in opposite directions, they reinforce each other in between them, creating a stronger field in between, but could get some partial cancellation way up here above both wires and way down here below both wires. Okay, anyway, so wire 2 is creating that blue field. Wire 1 is sitting in that blue field, so let's do Filb for wire 1. I cross B, IL cross B. The B from wire 2 is into the page, so IL cross B points up. The force on wire 1 due to wire 2 is up. And if we go through this same mathematical argument over here, we'd find that those forces are equal in magnitude, just as these over here are equal in magnitude. So Newton's third law, force pairs, Newton's third law, force pairs. And these two wires repel each other. So another interesting phenomenon. Parallel wires carrying currents in opposite directions will push apart from each other. So if you were trying to bundle these two wires together, say in a cable that was delivering power to an appliance, there would be some tension in that surrounding insulation as these wires tried to pull each other apart or push each other apart, just as these wires over here pulled themselves together, forming a tight bundle. Okay, so some more consequences of these kinds of forces between current-carrying wires. Example 3. A loop of current in an external B field. So suppose current is circulating counterclockwise around this loop here. We've got a B field pointing out of the board. Any given section of it, like a little section right here on the side where the current is pointing in that direction, so there's a little dl in the direction of our current, so we have a little IDL pointing up that way. Let's do Filb, IDL cross B. IDL cross B points to the right. This little section of the wire here is going to be feeling a force due to magnetism, Filb force to the right. What about this little section where DL points that way? IDL cross B, that'll be pointing up. This little section, IDL cross B, points left. And likewise down here, we'll find that IDL cross B points down. So this loop is going to be sort of stretched by carrying current in the magnetic field. It will be under tension as the loop tries to expand as the current runs through it. Over here, if we reverse the direction of the current in that same loop and look again at those points, here we would have our IDL pointing down like that. So IDL cross B points to the left. This little section feels a force inwards. This section is an IDL cross B pointing up, and so on over here and over there. This current carrying loop would be compressed as the current runs through it. The magnetic forces would tend to kind of compress and shrink and try to collapse that loop. So just by reversing the direction of the current through the loop, we could get this loop to ultimately stretch out and compress. That might have useful applications. Okay, last thing. We can kind of come full circle to the beginning of our discussion of magnetic forces, back to the force between magnetic dipoles, which we kind of avoided at the beginning as we focused on the magnetic forces on moving point charges only. But now, if we come back to our current loops, which we know represent electromagnets generating these dipole magnetic fields, then this current loop with the current circulating like this, out of the board, into the board, out of the board, into the board, has effectively a north pole here and a south pole there. North pole where the B field lines emerge, and a south pole where the B field lines dive back in. If we put that loop next to another current loop carrying current in the same direction, so out of the board, into the board, out of the board, into the board, so that one has a north pole here and a south pole here. So we have two magnetic dipoles. Let's look at nearby sections of the wire. Like this top section right here, carrying current out of the board, and this nearby top section over here, also carrying current out of the board. Those are like little sections of parallel wire carrying current in the same direction. And as we showed on the previous page, parallel wires carrying current in the same direction attract each other. That little bit of wire will attract that little bit of wire with an attractive force. Likewise, the bottom little bits. This bit is carrying current into the board, So is this bit here carrying current into the boards, those two little parallel pieces of wire, both carrying current in the same direction, they will attract one another. And the same will be true for any two opposite bits of wire on these two rings. These rings, these loops, will feel a net attractive force towards each other. These dipoles with their north and south poles, opposite poles facing each other, will attract. This explains why our bar magnets here, these bar magnet dipoles with their north and south poles facing each other, why they attract as well. It's really due to that Filb force. The magnetic forces on the free electrons in here, those magnetic forces, their magnetic fields exert forces on the free electrons, and the free electrons sort of drag their neighboring ions along with them. So this attractive force is that electric force due to the binding between the metal ions and the free electrons. Okay, so to say it one more time, it's the free electrons feeling magnetic forces, but they get kind of tugged away from their neighboring ions, and they drag their neighboring ions along with them. So this attractive force between magnetic dipoles is really due to the ions being dragged by electric forces due to their binding to the free electrons, which are feeling magnetic forces. Here's the reverse situation. If we've got these two current loops with current coming out and in, here out and in, so these currents are running in opposite directions. So it's like we have two electromagnets, two magnetic dipoles with their north poles facing each other, so like poles facing each other, B field lines coming out like this. In this case, this little section of wire here carrying current out of the page, and this little section of wire right here, these neighboring sections of wire are carrying currents in opposite directions. They therefore will behave like little bits of parallel wire carrying opposing currents, and they will repel each other. Likewise, these little bits here carrying opposing currents will repel each other, which is analogous to our bar magnets with like poles facing each other repelling one another. We know that these magnets would push each other apart and they would speed up, so clearly work is being done, energy is being transferred. That energy transfer, that work being done, is the work being done by the electric forces on the ions that are dragging the ions along with their free electrons who are moving and feeling magnetic forces. Okay, so the long story is that, long story short, it's still true that magnetic forces do no work. Or B fields do no work. They cannot speed objects up or slow them down. They cannot transfer energy. So whenever you see magnetic dipoles pushing or pulling on each other, it's actually hidden electric fields. The E fields binding the ions to the free electrons, doing the work that makes your magnet leap onto and stick to